Dee and I have been working on including some Boussinesq equations into GeoClaw. This is built on, as he said, G1's work from years ago, but that part wasn't adaptive. So now I'm going to talk about the part that did just enter GeoClaw with adaptivity about a year or two ago. So just to show you the difference it makes for those who are not familiar with the Boussinesq equations. This is a propagating Gaussian. On the left is the shallow water equations, and on the right are the Boussinesq equations. We use the SGN, Sergui-Najdi version. And what you see is that the shallow water travels faster, it's further along. And the Boussinesq equations, the leading wave is not the largest. The largest amplitude is actually trailing behind. So those are some things that will be important in simulations. So the Sergui-Najdi equations are a mess. I'm just showing you them in 1D because it would take like 3 slides to do them in 2D. But what you see here, by the way, this is our second set of equations that we implemented. The Madsen-Sorensen equations was the first set. We spent a couple years on those, but I actually think they're unstable. Not quite able to prove it, but almost. Anyhow, so we turn to the Sergui-Najdi equations because there's actually some literature on it that we could follow and not get hung up. So here we have the 1D shallow water equations, and we add this term to the right-hand side of the momentum equation. And psi, this is the unknown variable. These are height, bathymetry, gravity, fairly standard terminology here. Psi is the new thing. Psi satisfies an elliptic equation here with really complex terms. The important thing is there are 2 psi derivatives. The right-hand side B has 3 derivatives. So it's tricky. Let's put it like that. So let's talk about how to solve it. First, I'm going to talk about how it's solved without adaptive mesh refinement, and then how we modify it to include adaptive mesh refinement. So for those who have not seen it before, the literature uses a splitting method. First, we solve the elliptic equation to find psi. That's at a given time level. We have the height, the momentum at time n. We solve for psi. We will then just update using the right-hand side of the momentum equations. And h itself, the height, not modified at all. Now we've gotten to this star term, and we can take a shallow water time step for the star equations to get to time n+1. So the second step just uses the regular GeoClaw finite volume updates. The literature treats the elliptic equation up here using finite differences. Now, so that would be this. The equations are just repeated down below so you see them. Okay, things to note here are there's no wave breaking in the Boussinesq equations. At the moment, what we do is switch to the shallow water equations near the shore. If any cell in some 3x3 neighborhood, that would be the finite difference neighborhood, has a height less than the threshold. Okay, so that prevents us from doing differencing on shore when h goes to 0. That's not really stable. Plus, until there's a good wave breaking criteria, this is our substitute, since the shallow water equations do sort of model wave breaking by turning it into a traveling bore, which will decrease. So the boundary conditions that we use are the same as in shallow water. So it's either an extrapolation condition or a wall boundary condition. And as I said earlier to Maria, we do hope to improve those. Okay, so now we actually have a linear system to solve for the psi elliptic equation. And I am happy to refer to PETSI, where we use a Krylov solver with an AMG preconditioner. And the nice thing here is that Barry Smith extended PETSI so that we could use it with OpenMP. Since PETSI is a pure MPI-based parallel solver, uh, he built a version, so anything after version 3.21 allows an OpenMP program to call the PETSI solver. So that was instrumental. Okay, now how do we merge this into our adaptive mesh refinement? So first, some AMR basics. Here are the important points that had to be dealt with. We have, as you know, if you've used it, patch-based mesh refinement with subcycling in time. So here, for example, we have a coarse grid, which is divided in two for parallelization, so that each one is farmed out to an OpenMP core. Now here we have two fine grids, and you'll notice that this grid spans two coarser levels, no problem. I mean, two coarser grids at the coarser level. We also refine in time so that to get, if the refinement is by 2, as shown here, we take 2 time steps on the fine grid so that everybody gets to the same point later in time. Now, to get the ghost cells that are needed, we have to do space-time interpolation. So this intermediate grid over here will need ghost cells to take the next time step with the shallow water equations. So we need the time step at the last time on the coarse grid to do space-time interpolation for the intermediate grid. And you need that before you can take this next time step. So what has to change for using adaptive mesh refinement with SGN? Well, here's a few things. Some minor ones first. The linear system that we build includes all patches at the same refinement level. So here it's a global grid on the coarses level. It's global. But what do you do in the intermediate levels? Well, again, we need space-time interpolation, but now we need it for psi. That was not one of our conserved variables, which are h, the momentum. So we have to actually do another solve on the coarser level that we can do space-time interpolation to get psi to fill in the ghost cells at the intermediate time. That means we had to do a second elliptic solve, but it's only on the coarse grid and not on the finest level, so that does save you. And then we explicitly build the matrix in compressed row storage format and call PETSI with the ghost cells and all the equations and solve on a given level. And this fits in nicely, the AMR interpolation in the ghost cells. We just add psi to the vector of unknowns. Psi is actually going to be psi1 and psi2 because there's one for the x and one for the y directions. So we've added 2 variables to the vector of unknowns. Just to show you what it looks like, here's a comparison with what if we had a global solve at the finest level compared with some solves with subcycling in time and a composite AMR, which I implemented, and it all looks very close. You can see some changes from the uniform fine grid, but we feel that the cost is worth this in the cost savings by not doing the global solve and using mesh refinement. And here is just a quick last example to show what happens with, instead of the first example I showed of just a Gaussian expanding across a flat domain, here is actually a real calculation with bathymetry of our hypothetical asteroid ocean impact, because that's the motivation for me, at least, for doing this. We got initial conditions from Daryl Robertson, who happens to be here, I hope, watching, of using an ALE simulation. Here's the after 251 seconds, here was the height. We start with that and we place it in the middle of the ocean, wherever we want. So this is off the coast of Washington, where we placed our hypothetical asteroid. 5 levels of refinement to start, seen here colored in different colors depending on the level. 7 letters total when it reaches shore. So we got down to 10-meter resolution. And just here are some intermediate refinements. You see here, we are not tracking the outgoing wave, so it is greatly coarsened here. You can't really see it at this level, but these are fully tracked. And what we see here approaching the shore, we have soliton fission, which is a sign of the dispersion fighting with the nonlinearity. So this is a sign that your SGN equations are working. And here we see the asteroid has completely overtopped Grays Harbor Peninsula in about 50 minutes after the asteroid has hit. Okay, final thoughts. We do have some algorithmic issues. We, as I said, need a better wave breaking criteria than just the bathymetry offshore. I also would like the better boundary conditions I mentioned earlier with less reflection. I'm trying to investigate higher order differencing, which also might help with reflections, because as I said, we have second and third differences. So it'd be nice if the method itself is a little higher order. The boundary conditions for SGN, faster linear system solver would be nice. Maybe better preconditioners. And my hope is to actually be able to run using ForestClaw, which we'll hear a talk about tomorrow, which is an MPI-based, it's MPI-based built on top of pForest. It's a quadtree-based refinement, but it also has ClawPack, ClawPack GeoClaw propagation built in. And also on the list is to combine things with GeoClaw for modeling dispersive landslide tsunamis, when you'll hear about that tomorrow too. So that is